Hey y'all. In my previous video, I did a short demonstration on how to create a USB virtual serial port using a SAMD51 microcontroller. Unfortunately, the example code is fairly limited. And so in this video, I wanted to demonstrate how to create something that is more functional. The setup for this project will be identical to the setup from my previous video. So if you already know how to set things up, you can go ahead and skip this section of the video. Let's get going. First, go ahead and go to Atmel Start, and then let's go to Create New Project. Once again, I'm going to be using the Adafruit Metro M4 Express board, which has a SAMD51J19A microcontroller. So go ahead and search for your SAMD51 microcontroller in the list and select it, and then click Create New Project. Now, after the project has been created, the first thing that we need to do is configure the clocks. Go ahead and click on the Clocks tab on the left. We will then disable the external crystal oscillator. And we are going to enable generic clock generator 1, and we will configure it to use the 32 kilohertz internal oscillator that is in the SAMD51 microcontroller. Then we're going to enable the digital frequency locked loop, and we're going to configure it to use clock generator 1 as its reference clock source. After that, we'll go ahead and configure clock generator 0, and it will use the digital frequency locked loop as its source. And now we have the CPU clocked at 48 megahertz. Now we need to go ahead and add the USB stack to our project. So go ahead and click the plus icon by components, and then expand the middleware menu and go down to USB stack. And we are going to select USB device CDC ACM. Go ahead and click Add Components. That will add the USB stack to our project, and notice it is also clocked at 48 megahertz. So now let's just go back to dashboard. Just make sure that we have our component signals set correctly here, and then we're going to go ahead and rename this project. SAMD51J19A. You can name this whatever you want. Okay. And after we've done this, you can click Export Project, and then we'll go ahead and download the pack. Okay, go ahead and click on the file that was downloaded, and it will open up in Atmel Studio and create a new project for us. Okay, you can name the project whatever you want. Go ahead and choose the location where you want it and click OK. Okay, now I'm not a huge fan of developing in Microchip Studio. I prefer Visual Studio Code. So you definitely don't have to do this if you don't want to, but I'm just going to go and open this code in Visual Studio Code because I prefer to edit the code in there. Okay, so first, go ahead and open up USB start.c. And of course, this is where all the main USB serial port code is located right now. Go ahead and scroll down to the very bottom. At the very bottom, there's this function USB init. This function is actually called by the Atmel Start init function in the main function of our code. And it does a lot of the initiation work for our USB serial port. We then, in our previous video, we called this example program, right? And the first thing that it does is it just waits for that serial port to be enabled. After it's enabled, we call this function, which registers a callback function called USB device CB state C. Now, unfortunately, this function is not very clear in how it's named. What essentially that name means is USB device callback state changed. So when the state has been changed, the state of the USB device has been changed, this callback function will get called. And then we register two additional callback functions here. One to respond to a read operation finishing, and another callback to respond to a write operation finishing. We then go ahead and we start an initial read operation. Now, because this is the echo program, what happens is when a read operation finishes, it calls this callback function, which then writes back out what we just read in. When a write operation finishes, we then call this callback function, which initiates another read. Okay, now I want to show you something. Let's go ahead and, similar to what we did in our previous video, let's go ahead and go to our main function and just call that example program, right? And now let's head back on over to Atmel Studio. And we're going to build the program and deploy it to our microcontroller. Now, after it's been deployed to the microcontroller, go ahead and open up the data visualizer. And let's go ahead and connect to our COM port that we created. And similar to last time, you can type a message and it'll be echoed back to you. Now, what do you think would happen if we went back to USB start.c and all we did was remove the initial ACM read call? I would think that it would only stop reading the input and therefore also not give us any output, and so there would be no more serial echoing going on. Let's see what actually happens. Go ahead and build this. Okay, I am back up and running. Go ahead and open the data visualizer tool. Now, go ahead and connect to the COM port. So what do you think will happen when we try and type something in and send it to the microcontroller? I would just expect it not to echo it back out to us because we never read anything in the first place, and so it just wouldn't respond to the input that we're giving it. But what will actually happen, not only does it not do anything, it actually causes the application to freeze. And this isn't just Microchip Studio. This is any application. that is trying to do serial communication with the microcontroller. So if you're using the Arduino IDE to do this serial communication or some other application to do the serial communication, if you don't call that CDC ACM read function initially, the computer that is trying to send data, or the application that is trying to send data over the serial line to the microcontroller, will just freeze, and you have to close out of the application. So that's what I'm going to do right now. Okay, so I'm back up and running again. Now, why does that happen? Why does the application on the computer that is sending the data over the serial line freeze? I don't have a full answer for you. What I do know is that this function, the ACM read function, it actually provides the buffer to the USB stack where the data gets placed. And if we don't provide that buffer, then there is literally no place for it to put the data. And so I guess for some reason, that just causes the application on the computer side to freeze. You would think it would cause problems on the microcontroller side, but it does not. It causes problems on the computer side, which is very weird. So obviously, this code is not very user-friendly, right? A user-friendly read function would be a read function that we can call or not call at any time. If we want to read data, then we call the function. If we don't want to read data, then we don't call the function. In this specific application, if we don't call this read function, it actually causes problems on the computer's side, because it causes the application on the computer to freeze if we don't call this function. So this function must be called in order for things to work properly. And that's not really user-friendly. That's not what we want, right? This is one of the things that we want to fix. We want to provide a user-friendly interface for the programmer to be able to call a read or write function whenever they want, or not call read and write if they do not want to at certain times. So for the rest of this video, I want to focus on developing out this code to create a more friendly interface to do reading and writing to and from this USB virtual serial port. Now we're going to model our interface off of a very popular one. It is the Arduino serial interface. Let's go ahead and just take a quick look at the API for the Arduino interface. Now, it is not my goal to write functions that mimic every single one of these functions that are used in the Arduino class. There's really only a few key functions that we need. The first one is available. We need to be able to know, are there bytes available to be read on the serial line into our application? The next function is begin, just to make sure everything is properly initialized to be able to use the serial port. And then we also want a read function to actually read data in from the serial line, and we want to be able to call this or not call it at any time. So the application on the computer side should not stall if we do not call this function. And then also a write function. We need a write function to write data to the serial line as well. So those are the 4 functions that I'm going to focus on implementing in this application. So let's go ahead and go to usbstart.h and let's define these functions. Okay, so the first function that we want is a begin function to initialize everything. We are going to call this function USB serial begin. Pretty simple. It won't take any parameters and doesn't return anything either. Then we want a function that returns the number of bytes that are available to read on the serial line. So we will define this to return a 32-bit integer. It will be called USB serial bytes available. And it also won't take any parameters. The next function that we want is a simple read function. So it will also return a 32-bit integer of how many bytes we were able to read, and it will be called USB serial read, and it will take parameters as an input buffer, and then the length of that input buffer. This is a place to put the data that we are reading in from the serial line. And then finally, we need a write function to write data out to the serial line. So we will call this USB serial write. And we will provide an output buffer, the data that we want to output, and also the length of the data that we are outputting. And that's our interface. These are the functions that we're going to implement, and we're going to implement these functions in USB start.c. Okay, so let's go ahead and copy our function signatures over to USB start.c. We're going to place them down at the very bottom of that file. Go ahead and create empty functions for each of these. Now, the first function is USB serial begin, and we already know what needs to happen here. It's basically what already happens at the beginning of our example program. For the example program, it just waits to make sure that the serial port has actually been created and enabled, and then it registers this callback to be able to handle any reading and writing operations being completed. So let's just go ahead and cut and paste that code right into here. And we can actually go ahead and just delete our example program. It's empty now. We're not going to be calling it. So it's gone. Now, this serial port, the CD/CDF ACM is enabled function. It'll return true when the serial port is enabled. It's been created. It's possible maybe it will never be enabled or created. Maybe this while loop will never exit. If you do not want this to be an endless loop, obviously you can implement some sort of timeout here in this function or other behavior based off of the functionality that you want in your application. But for now, we're just going to keep this as an endless loop. Okay, now let's go ahead and go up to the definition of this callback function right here. Now, I don't really like the name of this callback function. I think it's pretty hard to understand what this function is meant for just by looking at the name of the function. I mean, I look at the state_c, and I assume, oh, there must be a series of states like state A, state B, state C. That's not at all what this is meant to be. This function is meant to be read as USB device callback state changed. And so let's go ahead and just rename it to something that is much more meaningful to us as a programmer. So I'm going to call it USB device state changed handler. And to me, that actually tells me what this function is doing. So we're going to rename the function to be that, and we'll copy and paste the new function name to down here in our USB serial begin function. Now let's go back up to these functions here, and we're going to do some more renaming. So if you remember, this read callback occurs when a read operation has finished. Now, in the echo program that was being run for our example program, it just immediately went back and did a write operation. Well, that's not what we're going to be doing anymore because we're not writing an echo program. So we're going to remove that. Same thing for when we finish a write operation, it went back and started a new read operation. Well, once again, we're not doing an echo program, so that's not what we're going to be doing. Let's change the names of these functions as well. So for this function, we're just going to rename it as CDC read finished. And for this other function, we will call it CDC write finished. And I feel like those names are much easier to understand what is actually happening here, rather than using that bulk in and bulk out terminology, which honestly, most people aren't really familiar with that terminology. Okay, next, let's go up further in this file. And notice at the top of the file here, there are a whole bunch of if-defined statements. I really wish that they would do better indentation on this stuff because it's really hard to tell what's going on here. But essentially, they're defining some USB device descriptors, depending on whether this is a high-speed USB device or a full-speed USB device. And they're also defining the buffer size as well, based off of whether it's high speed or full speed. A high speed USB device can have up to a 512 byte buffer size, whereas a full speed USB device can only have a 64 byte buffer size. Once again, I want to rename this definition just because it has the word echo in it, and we're not creating an echo program right now. We're creating something different. So we're going to call this CDCD USB buffer size. Now, coming down here, we have a buffer that has already been created for us from that echo program. But as you'll notice, they created this buffer using an array of unsigned 32-bit integers. And the size of the array is buff size divided by 4. And that's because buff size, which is 64, divided by 4 is 16. And this is 32-bit integers, so it's 16 32-bit integers, which is 64 bytes, of course. We don't really want an array of 32-bit integers. I don't know why they used that. We want an array of bytes, and so that's what we're going to do. I'm actually going to change the name of this one more time. I don't really like the name that I chose. USB device CDC buffer size, I think, is a better name for this. Okay, now this, just for my own purposes, I just want it down here. I like having it below the control buffer declaration. We are going to change this. So now we're going to have a compiler aligned array of uint 8t, and the size of the array will be USB device CDC buffer size. Okay, so the next thing that I want to do, so we already have these callback functions that we've written for handling when a read or a write operation finishes, right? But we also need to write some functions to actually initiate these read and write operations. So first, let's write a very simple function called CDC read start that will initiate a read operation. And it's actually not going to take any parameters. And all it's going to do is return. We're going to call that ACM read function. It's going to return the result of that. And we're going to pass as parameters to the ACM read function our, let's see here. I have the wrong variable name, USB device CDC buffer. And then USB device CDC buffer size. So we're just going to return that in our read start function. And then we'll go ahead and we'll also write a function that initiates a write operation. CDC write. And then of course we'll take a buffer that needs to be output to the serial line, and then the length of that buffer. Okay, I just realized I named that variable wrong. There we go, fixed that name. We're going to write the CDC write function in a couple minutes. I'm not going to write it quite yet. I need to instantiate or declare a couple more variables that we need for our application. So we need some state variables here. Now, one of the first variables we need is one just to track whether we have initiated a read operation. And of course, this is going to be a bool. And initially set it to false. Then we also would like a variable that tracks whether we have initiated a write operation. And then one more bool that tells us whether we are currently connected to a USB host. Okay, now when the read start operation occurs, we're going to set pending read to be true. And when the read finish operation occurs, of course, we will set pending read to be false. And once again, similarly with the write finished operation, we'll set pending write to be false. And when we call the write operation, pending write will be set to true. All right, now I want to go down here, and we've already commented out this line of code. We're no longer going to call that, obviously, but we do still need to make an initial read call. If we don't make an initial read call, the application on the computer side is going to freeze. So we have to do that. This just isn't going to be the user-facing code, right? This is all going to be invisible to the programmer, to the user of this code. So we're going to call here CDC read start. And that will place a pending read call. And it'll provide that buffer for data as it comes in to be placed. Okay, now before we go on, we need to instantiate or declare a couple more buffers. And I just wanted to go over kind of the architecture, the design of why we're declaring these buffers. So I'm going to pull up a little image here really quick, just to explain what's going on. So we already have this buffer on the right side of the screen, the USB device CDC buffer. And that gives 64 bytes for the USB stack to bring in data that is being inputted from the USB host. The packet size for the USB stack is 64 bytes. That is always going to be 64 bytes, but it doesn't necessarily mean that the data coming in is going to be 64 bytes. It might only be 5 bytes, right? And when that data comes in, these functions, they'll already tell us how many bytes are coming in. So if we go back and look at our code here, you'll notice on CDC read finished, there is a count parameter. And that count parameter will tell us how many bytes actually came in, and it'll be anywhere from 0 to 64. Going back to our image here, We always have to have a read operation pending so that this buffer is available for the USB stack to use. But the user may or may not be actively calling the read function, and they may or may not actually ask for that data that's coming in. So what we're going to do is all the data that comes in to this buffer, we're just going to transfer it to another buffer that we're just going to call input buffer. And this input buffer is going to be private to this API that we're writing right now. And whenever the user application wants the data, they will call a read function which just grabs the data from this input buffer that we're storing. So once again, the data is coming in from the host. It arrives at the USB device CDC buffer variable. We're then going to transfer that data to our input buffer variable so that this USB device CDC buffer can be reused for the next frame, for the next packet in the USB stack. And when that happens, let's say some more data comes in, we'll just take that new data and tack it on to our input buffer again. And then whenever the user application wants, they can just ask for that data and we have it ready for them in the input buffer. Now, the USB device CDC buffer, once again, must be 64 bytes because that is the packet size for the USB stack. This input buffer can really be any size we want, honestly. But we're just going to keep it 64 bytes for now. And then, of course, the user application buffer, that doesn't really matter to us right now. Every application is going to be different. Just whenever they call read, they will provide a buffer for us to put data into, and it'll be whatever size the user tells us it is. Okay, so let's go ahead and define that input buffer that we just talked about, in which we will store all the data that has come in over the serial line. And a lot of people, when they do this, they use what's called a ring buffer for their serial API. I'm just going to go really simple. We're just going to use a regular array, and we're just going to store a length of how much we've actually filled this array with. So we're not going to use a ring buffer right now. But if you want to make improvements in the future, you can definitely go ahead and use a ring buffer in your own code. In addition to the input buffer, let's go ahead and also declare an output buffer. A separate buffer that we are going to use for placing data that we want to output to the serial line. And we'll go ahead and we'll maintain a length for that as well to know how many bytes we are currently using in our output buffer. Okay, so now the next thing that I would like to do is go ahead and completely implement this function here, the CDC read finished function. Now we already know when we call CDC read start, we provide this buffer to the USB stack to place data that's coming in. When that transfer finishes, this function here, CDC read finished, is called, and we're given a count variable which tells us how many bytes were actually transferred to the USB device. So let's go ahead and implement this function. What we're going to essentially do is we're going to take those bytes from that buffer and we're going to transfer them to this other variable that we declared called input buffer, assuming that we have enough bytes available in input buffer to store the bytes that have just come in. So first, as you can see, we're already returning false here, indicating there's no error, but we need to actually do some error checking in this function. So I'm going to declare a Boolean variable just called result, and we'll initially set it to false. And then at the end of the function, we'll return the result. Now we are going to first check and see if the USB transfer finished. And so if the current state is that the USB transfer has finished. We're going to go ahead and execute some code. And in that state, we will set pending read to be false. So we have finished the read. And now what we need to do is we need to figure out first how many bytes do we have available in our input buffer in order to store the new bytes that are coming in. So let's go ahead and declare another variable that we will call input buffer bytes remaining. And it's simply equal to the buffer size minus the current number of bytes that are being stored in our input buffer, or input length is that variable. Okay. Now, let's go ahead and enter a critical section of the code. And this is basically going to tell the processor that we do not want this code to be interruptible. Okay. Now, while we're in this critical section of code, we're going to transfer these bytes from that buffer that we gave to the USB stack into this other buffer, the input buffer variable that we declared. So if the number of bytes that came in, which is the variable count, is less than the number of bytes that we have available, then we will go ahead, we should really say less than or equal to, we will go ahead and we will copy those bytes to our input buffer. I'm just going to do this with a simple for loop. So we're going to grab the byte and then we're going to append it onto our input buffer. Then we're going to increment the length of our input buffer, indicating that we're now storing one additional byte in that buffer. And then if, we'll just do some basic error checking here, if the input length is now equal to the buffer size, let's go ahead and break out this loop. We don't want to exceed our buffer size. Okay, now in the scenario that the number of bytes that have come in is greater than the number of bytes that we have available in our input buffer, let's go ahead and just set the result to be true, indicating that there was some kind of error that occurred. We just didn't have enough space to store all those bytes in our input buffer. All right, now after we've done that, let's go ahead and take that buffer that we provided to the USB stack, and we're just gonna set it back to all the bytes are going to have a value of 0. We're reinitializing those bytes to be 0. And now we're going to leave our critical section, telling the processor that it's okay to interrupt the code again if need be. And finally, we always need to go ahead and do another read start at the finish of this function, because remember, if we don't have a read pending for the USB stack, if that buffer is not available, then the application on the computer side could actually hang when it tries to send serial data to the microcontroller. Okay, and that is the completion of this function. Okay, let's go ahead and go down here to the CDC write function and fill this one out, fully implement it. So at the CDC write function, we've been given a buffer by the user of the bytes that want to be outputted to the serial line. And we also have a length, which is the number of bytes that we want to output. This one's going to be a little bit more straightforward than the read function. So first, let's just go ahead and iterate over the buffer that the user would like to output. And we're also only going to maintain this loop as long as the connection is active as well. Now we're going to grab the current character or the current byte that we're looking at. And if this byte happens to be an end line character, or if the current number of bytes that we're storing in our buffer reaches the maximum buffer size that we have, we're going to go ahead and flush the buffer out to the serial line. So it's actually we're gonna initiate the USB send operation. So here, we're gonna call the ACM write function. We're gonna give it our output buffer and the number of bytes that we have. And then we're gonna wait for that operation to finish. Then we're gonna reset the number of bytes being used in our output buffer to 0. And then, assuming that there's more bytes that still need to be output, when this operation finishes, this loop will continue and it'll transfer those bytes to our output buffer. Okay, and then at the end of this function, we'll just return the number of bytes that we were given to send. Okay, now we need to go ahead and implement the functions that are visible externally to this person that is using this API. And those are these functions right here. So we've already done the USB serial begin function. Now let's go ahead and do the USB serial bytes available. So here, let's first just check and see if there's already a pending read happening. If there's not, let's make sure and start one. And now all we really do here is return input length, which is the number of bytes that we have in our internally stored buffer right now that we could return to the user. That's it. For the USB serial read function, it's going to be a little bit more involved. So first we're going to declare an integer variable called result, and result will be the number of bytes that we actually copy from our internal input buffer into the user's buffer. I actually just realized that naming is probably not ideal. So we'll go ahead and call this user input buffer, and might as well call this user output buffer. Okay. Now, if we have bytes in our internal buffer that are available to be copied over to the user, let's go ahead and figure out, based off of how much space is available in the user's input buffer and how many bytes that we have to copy over, how many bytes we are able to copy. So first we're going to declare a few variables. First will be the number of bytes that we have to copy over, which is bytes to copy 0. Then we have bytes remaining, which is how many bytes will be left over in our input buffer after we finish this operation. Then we're going to call another variable called index of the first remaining byte. Now, if the number of bytes that we have in our internal buffer is greater than or equal to the number of bytes that are available in the user's buffer, the number of bytes to copy is simply the length of the user's input buffer. Because we don't want to copy more bytes than they have available for us to copy. And then the number of bytes remaining would simply be the number of bytes that we currently have available to copy minus the length of their buffer. Finally, the index of the first remaining byte is the length of their buffer. It's equal to that. All right. Now, if the number of bytes that we have available to give to the user is less than the size of their buffer, then we just say bytes to copy is equal to the number of bytes that we have available to copy. Okay. Now we'll go ahead and set our result to be bytes to copy, the number of bytes that we actually plan on copying to the user's input buffer. At this point, let's go ahead and enter a critical section. Once again, telling the processor that we do not want this code to be interrupted. And we will copy bytes from our internal buffer into the user's buffer. Oops, I used the wrong name there. Here we go, user input buffer. After we copy those bytes, if there are any bytes remaining in our internal buffer, let's go ahead and shift those bytes so that they are now located at the beginning of our buffer. And then we will set all the remaining bytes in our buffer that are not currently being used to 0. And now we'll set the input length, which is the number of bytes that we're currently storing in our internal buffer, to be bytes remaining. Now, if we don't have any bytes remaining, then let's just go ahead and set the entire input buffer to be 0. At this point, we can tell the processor that we are done with our critical section. And the last thing that we need to do is we just need to make sure that there's another pending read occurring. Okay, and that is our read function. All right, let's go ahead and implement our USB serial write function. This is actually going to be the simplest of all of them. Actually, all we do is we just go ahead and call the CDC write function. And we give it the user output buffer and the length. And that's it. Okay, before we go build this, I actually just realized I named this variable wrong up here. So let's go ahead and rename that input buffer, not just input. Fix that error. Before we build this project, I actually found a couple bugs in my code that I need to fix really quick. So if we go up to the USB device state changed handler function, I added these two lines here. So we need to make sure that we have those two lines to set that CDC connected flag to keep track of the connection status. In addition to that, if you go to the CDC write function, I had this line missing here. We were supposed to copy what was from the user's buffer into our own output buffer, and then increase the length of our output buffer as we do so. So I went ahead and I added that line right there. And after having added those lines, we can now go to our main function and we can write a program to use this serial API that we just wrote. Okay, so if we go to our main function, the first thing that we want to do is simply call USB serial begin. This is similar to how in Arduino you would call serial.begin. Now let's go ahead and define our own buffer that we will use in our application to store data that comes in from the serial line. So we'll just call this user buffer. So we'll make the length of it equal to 64 bytes. And let's just go ahead and initialize the memory to 0. Okay. Now, in our while loop, we will simply check if there are bytes available on the serial line. And if so, we'll go ahead and we'll do a USB serial read. And then we'll go ahead and, I guess this is somewhat similar to an echo program, but it's obviously with this API, it's much more expressive and we can do a lot more. But we'll just go ahead and say we'll just say received, like that. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters or 10 bytes. And then we will output what we received. Then we'll go ahead and we'll output a end of line. And let's go ahead and after we output what we received, we'll once again reset our application buffer to be 0. All right. Okay, now if we switch over to Microchip Studio, we can go ahead and build the solution. And then after you finish building, let's go ahead and deploy it to the microcontroller. And now go ahead and go to the Tools menu and open up the Data Visualizer. And let's connect to the COM port that was created. And we type a string such as hello, and it echoes that back to us, but with that additional output that we put on there. And that's it. So what we've done here, of course, the actual application that we've written is pretty similar to that echo program, but we've written an application that has easy read and write functions that can be used at any time. And if we choose not to read anything, that's perfectly okay. It's not going to cause the computer application to stall or hang when it tries to send serial information to the microcontroller simply because we did not call USB or simply because we did not call the read function. So that's about it. Obviously, this simple API that we've written here is not a perfect API. It might even have some bugs in it. But for now, it gets the job done. And I'm sure you can take it and improve upon it. If you have any questions, feel free to ask me.